Good morning. This is Bob Meijer from TKI Offshore Energy. Today's Studio Offshore Energy, our regular webinar, is about wind farm optimization. Now, this is a topic, of course, that is very close to our hearts, especially in these times where we're looking at cost and revenues of offshore wind farms and complex business cases. So today we have a presentation which is based on a study that was performed on our request by DNV about wind farm optimization. We have in the meeting Menno Kloosterman of DNV, who will present the results of the study. And following that, we'll have a discussion on a reflection on the study as well, where we have invited Tom Willems of Vattenfall to present his view on this. So, Menno, the floor is yours. Please start your presentation.
Great, thanks. And I'm assuming I'm doing this in English?
Yes, we do. Yes.
Yes. Okay, great. I'll share my screen again.
And just to make sure, we are recording this webinar, so that you are aware of this. Yeah, please,
yes,
Menno, go ahead.
Yes.
Yeah.
Can you all see the screen? I hope. Yeah. So thanks for inviting me, and yeah, I'll give a brief let's say overview of the study we've been doing. I think about a year ago now. Can't exactly remember when we closed it. But yeah, we were approached by RVO to study the possibilities to increase the capacity factor of offshore wind farms, of future offshore wind farms, and to see how can offshore wind farms better tie into the energy demands and give a more stable, less volatile output. Because yeah, as we all know, and as we see today, that there's a lot of course, a lot of installed capacity and a lot more planned installed capacity of renewables. But yeah, we see issues with congestions and mismatch between demand and supply. So in order to tackle this study, we already encountered our first challenges to properly define capacity factor, and we'll come to that in a bit more detail later. But we've decided together with RVO to look at two capacity factors, basically a long-term and a short-term capacity factor. I'll explain the definitions a bit later on. So for this study, we have looked into several strategies to improve this capacity factor of offshore wind farms. We looked at energy conversion concepts, we looked at storage, and also interconnection concepts. And in order to, let's say, narrow down our scope, we have come up with a methodology that's outlined on this slide here. Yeah, to ensure that we don't have too broad of a scope, given the budget and the time we had for this study. So we started with a kind of concept identification phase, where we had a total of 11 concepts, which we evaluated in a more qualitative sense. And based on those initial evaluation, we narrowed down our search to 5 concepts. And these top 5 concepts were then detailed a bit more in depth, where we kind of reevaluated some of the KPIs that we defined at the first phase, also in a more quantitative sense where possible. And from that reanalysis, we derived the top 3 of concepts. And for those top 3 concepts, we then did a more qualitative sensitivity analysis if you change certain optimization parameters, how would that, in a qualitative sense, change the potential outcome of the results? Finally, we also looked at, what is knowledge gaps and innovation opportunities for these concepts. So the key performance indicators, or KPIs, that we looked at is the following 5. So we looked at, obviously, cost. So what is a change in capital expense between the different concepts? What is, of course, the impact on the capacity factor? But also, what is the energy efficiency? So certain concepts, although they could increase capacity factor, will come at a large cost in terms of energy loss. Another one is environmental impact, space use offshore. So do we need a lot more space in the already tight North Sea, for example? That could result in a low score there. Finally, the technology readiness level was assessed in a more qualitative way. And in addition to these 5 indicators, we also added weights in agreement with RVO. So we agreed that we would weigh the costs and the impact on the capacity factor with a factor of 2 relative to the other 3 KPIs. Right. In terms of the definition of capacity factor, that was already a discussion on its own. In agreement with RVO, we have used 2 definitions. For the short term, we would say that is the capacity factor calculated over a short period, so like this time scale of minutes and hours. So this gives more of an indication of the let's say short-term fluctuations in power, and perhaps gives can be used more how much short-term fluctuations will there be in the power output of your energy farm or offshore wind farm. Whereas the long-term capacity factor is more calculated over like a year. So this average, of course, averages out a lot of fluctuations, but gives a more indication of the asset performance over a whole year. What's important to note here is that we also defined the long-term capacity factor as as in this equation here, where we gave the energy delivery onshore, including all kinds of curtailments and losses, divided by the installed capacity of the wind farm. So the reason for that is that we wanted to improve the capacity factor of the wind farm. So we would always refer to that wind farm installed capacity when computing the capacity factor. And that's important, as you might see in the concepts that we looked at. In terms of the in the trade-off, the initial phase, for each of the KPIs, we next to the weight we assigned a score, and that we did by looking score from 1 to 5 for each of the KPIs, where for example, for costs, if you see a significant cost increase more than 30%, this would get a score 1. On the other hand, if it would be a more capex neutral or even reduction compared to a base case, you would get a score 5. So another one, for example, the reduction in long and short-term capacity would give you a score of 1, whereas if the concept manages to improve both the long and short-term capacity factor, that would result in score 5. So that's how we in this initial phase, did a qualitative or semi-quantitative weighting and scoring of each of the concepts. So that's on the methodology. Then looking at the concepts that we looked at, the initial 11. I'm afraid it's a bit of a boring list, but the concept consisted of a couple of, let's say, concepts with wind and solar generation. So we had the concept where we add solar capacity offshore with the assumption that it's complementing each other in terms of energy output. One very obvious solution that's already kind of standard in the offshore is to increase the rotor area. So a relatively large rotor compared to the installed capacity already improves the full load hours and the capacity factor. Then we had a slightly more exotic concept of using the electricity directly to charge, let's say, offshore platforms or become a charging point for ships. Then we had two concepts with battery storage, one where the battery is located offshore, one where the battery is located onshore. Then, three concepts with hydrogen. So one where the wind, the electrolyzer is stored offshore, and also storage of hydrogen offshore. Then there's a concept where the hydrogen is generated offshore and transported via pipelines. And then one where the electrolyzer is located onshore. And one, slightly more exotic, where hydrogen is used directly for fuel ships and platforms. And two slightly more exotic concepts. One is the one where we look at compressed air, so subsea energy storage. Ocean Grazer company, not too far from the city where I live, was quite far in this concept, although fortunately they discontinued quite recently. Another very exotic concept would be where you create some kind of very large water basin where you could create an artificial height difference to pump water to a greater height and store it. Slightly more exotic concept. Yes, so looking at these concepts and doing the scoring and the weighted scoring, you can see the results in this table below, where we found a top 5, or rather a top 6, where one of the winning concepts was actually the one where we use offshore, let's say an offshore power station, where ships or other platforms can use the electricity directly. But in agreement with RVO, we decided not to look more into this concept because of the uncertainty whether this concept really is feasible in practice and if there's enough demand for such a solution. So then we decided to carry on with wind and solar offshore, the larger rotor concept, battery storage offshore and onshore, and the hydrogen conversion offshore and supply to shore. That's the 5 concepts we evaluated in more detail. Then an important bit of information is the assumptions, because obviously it's very easy for each concept to do an optimization study in itself, and with the time and the budget we had, that was not feasible for us. So we had to narrow down and lock in some assumptions to keep the work within reasonable amounts. So that's listed here. So, for example, the base size of the wind farm is always 2 gigawatts. And then for each concept, we have pre-selected based on our experience or assumptions, a reasonable ratio of for example, solar. So we assumed 900 watts of megawatts of solar. In the case of the hydrogen concept, we assumed that 2/3 of the energy of the capacity would be the electrolyzer, and then 1/3 still the export of electricity. In case of the battery concepts, we had a standard battery output power of 300 megawatts with a 4-hour capacity, where you can see here that in case of the battery offshore, and that's an important assumption, we wanted to distinguish between onshore and offshore battery storage. And we therefore deliberately reduced the cable capacity in case of the offshore battery offshore storage.
Menno, I'm also looking at the clock, and I think this material is of course very important as the basis for the conclusions that you're going to draw.
Yes.
But I think in the sake of time, it would be good maybe to go to the conclusions. So we have some time left for reflection. And of course, the report will be available for review for everybody.
Exactly.
All the underlying assumptions can also be reviewed later on.
Yeah. Thank you. Yes, I see already that time is flying. I will jump forward to maybe the top 3 that we found from the kind of reassessment. And from this, we found that the battery onshore was a winning solution in this sense, followed by the larger rotor. And finally, the wind and solar offshore. So what was, and maybe that's on the next slide here, we did see some quite big changes in some of the scores that we initially assigned to certain concepts. Whereas, for example, the hydrogen concept on the CAPEX, we gave it a pretty high score initially, and we found, for example, that this is a very expensive concept, and the same holds for wind and solar offshore. So, of course, for solar offshore, the information is, of course, a bit limited on CAPEX, but as far as we could see, that's also a very expensive concept. So, that was a big takeaway in terms of the results. That once we did a bit more deep dive, we could see quite some shifts in the initial scores that we gave. And the reason is also in some concepts explained that it depends strongly on what was the initial concept that we looked at in the qualitative phase. Whereas, for example, for hydrogen, certain studies showed that if you replace the export cable with a pipeline, and it was a certain German study that we looked at, and is also referenced in our report, that would have been a very cost-effective solution in that particular case. So it's also very strongly dependent on your reference frame and what's your assumptions, and in terms of what becomes a winning solution. And I think that was in the end jumping to the conclusion, also our main conclusion. So we did find methods that could achieve a higher capacity factor. For example, battery storage, onshore, offshore, hydrogen production was, in our view, challenging in terms of the cost and the energy efficiency. And I think, the challenge is also to do a proper sizing of all of these assets in an energy farm and do an optimization, and which is of course something we hadn't been able to do in the short time span of this study.
Yeah, clearly. Yeah. Thanks very much, Menno, for the explanation of the study, and also the I would say striking results, because as you explained initially, there was a different view on where these options would go, and the study gave I would say new insights in efficiency and cost of the various options. So also for me, it's a very interesting and surprising, partly surprising outcome. Thanks very much for that. We also have a bit of time for reflection. Not so much Q&A from the audience. I think if you have further questions, you can always mail us with questions, so we can see if we can have answers to those mails, either from Menno or from other experts within the DNV team. We have Tom Willems from Vattenfall here. Tom, there is a bit of time left for some initial reflections from your side.
Yeah, thanks a lot. Good morning, everyone, and thanks for the report and the presentation, Menno, and also thanks for the invite to share some reflections to this report. I have two sets of reflections today. First, some general comments on the report itself and the approach that was taken, and then secondly, some reflections on some of the strategies that were analyzed. Starting with those general comments, I enjoyed reading the report very much. Treating a wind farm as an energy farm, as it was called, with multiple assets, resonates very much with the work that is happening at Vattenfall, and it's great to see that this topic is now being explored here today. That said, from a wind farm developer's perspective, there's typically a bit stronger emphasis on value creation and risk management than what was explored in this study. And of course, that's also related to what Menno already mentioned on the time and budget available. So fair point there. Next to contributing to a future that is fossil-free, companies also view energy transition as compelling business opportunity, and it could be valuable to also include more on why are these innovations attractive from a perspective of the industry that actually has to invest in them. My last general remark then is on the report does an excellent job on outlining the pros and cons, the technical pros and cons, very objectively. It gives less attention though to the practical realities, which is also of course more in the details. Taking reality factors such as regulations, risk, market signals, they often determine whether a project is considered investable. And then, of course, ultimately, what can actually be built. I think those factors play a key role in identifying the most attractive strategies. And could be valuable to also include in the discussion. Then some reflections on the strategies themselves. First, on the larger rotor surface, I think it's a very attractive strategy. Because also power prices are often very low at high wind speeds, where all the wind farms are producing at maximum capacity. Shifting production to lower wind speed is therefore interesting, even if that comes at the cost of some high wind output. However, this is really a design choice that only the OEMs can offer. And it comes then also at its own technical and financial trade-offs, like, for example, the lifetime of the wind turbine, which is then also interesting to consider. The hydrogen strategies, they are very promising, but also in the long term, they still depend heavily on political direction and really the commitment to scale. It's of course a bit a chicken and egg story there. And we do see individual projects moving forward, but only under the right conditions. And that's typically when developers and off-takers align on that commitment. And then the most promising one from my point of view is the battery storage. That's becoming increasingly important, especially as we have zero and even negative prices becoming more common. I think similar to what was concluded in the report, the battery is already a very good business case, not only to increase the capacity factor, but also to open up additional revenue streams from, for example, ancillary services and trading on the intraday market. However, including a battery into a wind farm has its own practical challenges. For example, in the Netherlands, we connect at the offshore substation. And that means that including an onshore battery in the project scope is actually not that straightforward, whereas in Sweden or in Denmark, that can work much easier. Final remark on the battery topic is that focus very much on future wind farms, and it could actually be interesting and valuable to also explore how batteries might be applied to existing wind farms to help stabilize the production profiles and generate additional value. So that's maybe some food for thought. Yeah. In short, the report provides a very strong overview of a highly relevant topic, and my main reflection is that to truly identify the most promising strategies and focus our innovation efforts, I think a deeper understanding of the business cases and the practical challenges is needed. I'm very excited to continue exploring that together, of course. So thanks again for the opportunity.
Yeah, thank you, Tom, for your reflections on the report. Also, very valuable insights again. I think if we look at the overall conclusion of the study of DNV and also your comments, I really think that this is a starting point to have a different view on how we can further optimize. So clearly, there are still things that need to be investigated further. But the study of DNV put us really in the direction of valuable opportunities to continue research and innovation. And this is very much part of the TKI Offshore Energy Innovation Program. So also this study guides us in a way to where we should aim our focus if it comes to further optimizing. And I also noted some of the remarks about the practical application, for example, given regulatory situations in the Netherlands compared to other countries. You mentioned also the connection point, for example, and where you could locate batteries if this is offshore or onshore. And these are details that need to be further, I would say, investigated. But it is extremely helpful to have some direction where the real opportunities are. And I think, Menno, you very well presented the method of your study and also the conclusions. I would like to thank you both very much, Menno and the DNV team, for the study that you've performed, that we're now sharing the results of, and also Tom for your comments here. I would like to thank very much the audience for taking out time early in the morning and to listen to what we had to present here. And I also would invite you to interact with us further. We've seen some notes already in the chat. But please continue to send us your remarks and comments so we can also continue to interact with yourselves. So I'm looking very much forward to the follow-up actions of this study, and it will definitely have impact on the way we look at research and innovation for offshore energy farms. So thank you very much for your attention, and
thank you.
Yeah, I hope you enjoy the rest of the morning.
You too. Have a great day. Thanks for your comments.
Have a great day.